So good morning, everybody. And what we want to do now is to try to link these discussions with the variances and these expectation values, which are going to calculate in the exercises, with something which has been floating over the surface. And we call this overfitting, underfitting, and then you have this bias-variance trade-off. So how do we link these different dots? How do we link, for instance, the calculation of the variance of the parameter beta, which we can calculate analytically when we look at ordinary least squares? What does this actually mean for us? And how do we link this with an understanding of overfitting? So these are the kind of overarching questions which I want to step you through today. So I'm going to sneak in a kind of mini lecture, and then with the exercises, which are more typical paper and pencil exercises, you will get analytical expressions, which you then are going to link with some of the questions you have in the project. So one of the questions which you've probably seen in the project is to plot the value of the parameters beta as you increase the complexity of the model. So what does this mean? Now, there is something which is a kind of a holy grail in basically all of machine learning, and it deals with overfitting, and there is a measure which is called the bias-variance trade-off. So yesterday we mentioned these resampling ways, which are ways to improve the quality of the fit. So I invite you to take a little look at this section here, because this will also be the weekly exercise next week, which you again can bring into the project. So the bias variance trade-off is a kind of measure, and we're going to discuss what it means. And down here, there are code examples. And one of these code examples deals simply with the bias variance trade-off applied to a given model as a function of polynomial degrees, so increasing complexity. And one of the things you will see, so this is the mean squared error for the test data, not the data included in the training. And there's something which goes like this: the bias, you will often see that in textbooks. This is the total mean squared error, the blue one. And then you see this variance. What does it mean? If you scroll down, there is another example which you can find in Scikit's website. And this is us fitting three polynomials to a data set which is a cosine here. So this is a data set you're making. And then you just fit a cosine to that one. And no, you fit a polynomial to that one. And there's a polynomial of degree 1, 4, and 15. Okay? And in this particular case, we have 30 data points. So it's pretty small. So as we said, the results will change as a function of the number of data you have. And one of the things you will see is something like this. And we are going to try to dissect what this means. So this is all training, not training, but applications of the mean squared error to the test data. So those which were left out from the training. So here you see the mean squared error for degree 1. Degree 1 is just a straight line. That's your model. The data are the blue dots. And the true function, no, so the samples are the blue dots. And the true function is the one here which you want to fit. Okay. Now, the fits which you make here get better and better. So with degree 4, you have a mean squared error which is 10 to the minus 2. So it's pretty small. This quantity here is the standard deviation of the mean squared error. So that is the variance of the mean squared error, but you take the square root of it. So this tells you that you have a mean squared error of 10 to the minus 2 plus minus an error. Then you go to degree 15, and you see that your model behaves wildly compared to the true function. And you see that the mean squared error is on the test data is just huge, 10 to the 8. And you have a standard deviation, which is also huge. So what you see here is that in this particular case here, your model does not go through the data points. Here, your model is doing better. Here, you have forced the model to go through every single data point, almost. So this is an example of overfitting. So these are the data points you're using in the training, the samples here. And then you see your model, the way that actually results in something which tries to go through basically all the data points. And when you apply this to points which were not included in the training, so these blue points are the points included in the training. When you do that, you just get crazy results. Okay? So this is an example of overfitting. And the question is, what does it mean? How can we relate this to these quantities which we need to discuss now? The bias-variance trade-off, which you will discuss in the project. What does it mean in connection with the variance of the parameters beta? Okay, so I invite you to take a look at these programs here, because they have in essence the kind of analysis you will need to do in project one. So let's move over to the whiteboard here. So the one of the things which we're going to do with these resampling techniques is actually to calculate the mean squared error after we've done the training on test data. So we are not so much interested in the mean squared error for the training, because we know that when we train with more and more complexity, we would get a pretty good fit to the data. So it's the test data which is interesting, because that tells us whether we are overfitting or not. And it's to strike this balance which machine learning in a certain sense is about, so that you can have a model which is reliable. If you overfit, clearly it's not reliable, because then you will fail miserably on many data, like you saw this 15th order polynomial which we were fitting. So the kind of things which we need to think, and which will be important for the both the exercises today, is to understand the overfitting. So overfitting is a central point. And then we have this resampling techniques, which we discussed yesterday during the lecture. And we will discuss them. We will wrap up this discussion next Monday, when we will discuss something which is called k-fold cross-validation. So yesterday we mentioned the bootstrap, which is a simple method to implement yourself. When it comes to k-fold validation, you should feel free to write your own code or use the functionality you have in scikit-learn, which I will come back to. So resampling techniques, and how does this relate? How do we analyze these things? How do we analyze, how do we predict overfitting? Is there a measure for that? So one of the things which we are typically going to do now is to have some training data and some test data. So we have a model, which we have labeled yi tilde. We have some training data. Let's call this T of I. And then we have the test data. So we have a little T of I, or tau of I. And then we have the output, which is y of I. So this is just for one data set. And what we want then is some error on the test data. So this is typically the thing we want to present. It's often convenient also to analyze the error on the training data, but the error on the training data is often something which is expected, in the sense that if you increase the complexity, you get an error which is smaller and smaller. Because the more complex the model, often the better the fit you make. So this quantity is now given by some function. Let's just call this L. And this is a function of y of I tilde, t of I, and tau of I. And the quantity we have been looking at till now is the mean squared error. So in our case, in project 1, it's typically the mean squared error. So we fit a model, and then when we plot this quantity, it means that the total error, and I'm just going to write this without the subscript test now. The total error is typically the sum over all the individual errors. And then I just write this L of y of I tilde, t of I, and tau of I. When you make a plot, using resampling techniques, for instance, so one of the typical cases you end up with is something which looks like this. So we've seen this many times, and you saw that in one of the exercises in week 35. So this is a function of complexity. And then we have the error. And this is normally what we call the predicted or test error. But it's common also to plot it for the training data. So let's plot both, just to remind ourselves of what you might see. So depending on the type of model you have, you can have something like this, and there will be a band here, because you can rerun this experiment many, many times. And typically then when you take the mean value of all individual experiments, you get an error here on the training, which can look like this. And you've seen this in the exercises for week 35. Then when we look at the test case, this often looks something like this. And then there as well, we can have a band of values, and we take the mean value of all the kind of measurements which we make. So bootstrapping is one of these cheap, poor scientist or poor practitioner's way of obtaining new data without making a new experiment. So where you just reshuffle the data with the replacement. And so what you would get then would be a band here, and you would calculate the mean value. So this would be the error test. And this is often the quantity you would present. So this would be the final one after either cross-validation. So we would typically have a resampling technique. The simplest one is the bootstrap. And there are many, many other ones, but the bootstrap is often used on small data set. And then we have cross-validation, which is another technique, which we will discuss in more detail next Monday. So the thing I wanted to bring up now, so this is a general type of pattern which you will see. And this does not apply only to the mean squared error, but it could be the same result for a classification problem, where you make a more and more complex problem and a complex training, and then you can get, for a classification problem, a similar behavior. So this is what you will see in project 1. The quantity we are interested in is normally the test error, because that's the one which tells you how well your model applies to a set of data which was not included in the training. As you know, you can, with training, just to repeat myself, you can just train a model to perfection by tweaking and fixing the functionalities and so on. And then you can get a train error which goes to 0. That's not the interesting case. This is actually the interesting case is actually this one. And you're often interested in a situation where this one starts to bend up. Because that's where you would typically say that here, I seem to have the best compromise between the complexity of the model and the data which I have at my disposal. Now, so how do we analyze this? So how do we analyze it? And one of these ways of doing that is the so-called bias-variance trade-off. And you will see that as a very common measure in many scientific articles, in many textbooks. So what does it mean? So let's take a look at the derivation of the bias-variance trade-off. So this is actually one of the exercises next week, but I want to link this with the calculation of quantities like the variance of both the output, which we are looking at, and the parameters beta, but also this type of analysis. So this is bringing in the concept of a variance, what it means, but then we're also going to introduce this bias as a measure here. So let's go slowly through it. So this is actually one of the exercises for next week. So we're anticipating a little bit the result. And one of the easiest ways of doing that is to look at the mean squared error. So this is often the quantity you will see in textbooks. And in project one, this is also the reason why we actually bring it in, because it's a good way to get some familiarity with these concepts. So we know that the mean squared error is written like this. So we have defined it as an expected value, n minus 1, and then we have y of I minus y of I tilde squared. And we can rewrite this now, since this is a sample mean. So it's actually the sample mean, which we rewrite as an expectation value. So all our expectation values are sample means. So we have only a sample of data. We don't know the probability distribution behind the y's. So what we do then is simply to calculate as best as we can this quantity here. And that's why these resampling techniques also are important, because it's a way, in a cheap way, to make new data from the same data set which we have. So this gives us then a y minus y tilde squared. So this is just a compact way of writing it in terms of vectors. And you've seen this expression before. So if I write it out, this is nothing but the expected value of y squared. And then I have minus, so I'm just multiplying out these terms. And then I have the expected value of y times y tilde plus e square root, no, not square root, but squared of y squared. Okay? So I'm just writing out, I'm just performing the multiplication. I hope you don't get offended here. Huh? Then, if I look at the quantity you have here, this is a quantity which I can rewrite as an intermediate step. So if you look at this quantity E, the expectation value of y squared, we can actually rewrite that as the variance of y tilde. And it's the variance of y tilde plus the expectation value squared. So if I take that one to the last term to the left-hand side, so this is the expectation value squared. So this is nothing but the quantity we called mu of y tilde squared. So that's the expectation value of the mean value for y tilde, the model we have made, squared. So this quantity you see here is going to tell us how much the model varies with respect to its own mean value. Okay? So this is just one intermediate step. So let's look at the other quantity, which we have this one and this quantity here, and just see how we can write them out. So if we now go to the next terms, then we have an E the expected value of y squared. This is the data which we have. And now we bring in the assumption we made, which is f. There is a function f, which is a non-stochastic function, plus some epsilon squared. That's nothing but that. So keep in mind that we have made an assumption about the data, that there is a function f, which we are approximating, and we have some noise. So these are the basic assumptions behind the derivations of the linear regression equations. So if we now rewrite this, we just write it out, and then we have f squared, the expectation value of that one, plus 2, and then we have the expectation value of f times epsilon, plus the expectation value of epsilon squared. Now, epsilon squared, we have by definition said that that's the variance of the noise. So the variance of the noise is something we have defined as sigma squared. Now comes a very important thing. So look at this term here. So we have said that f is a non-stochastic function. We are also assuming that there is a probability distribution which determines the stochasticity of epsilon. So epsilon is a stochastic variable. It's a noise, which we think is something you can either model or is inherent in the data. So there is always something which we cannot define properly. And when you run an experiment, like Ida here, who runs experiments at CERN, you know that then you know that you have to deal with the background noise or things like that. Sometimes you have a model for it, other times you don't have it, and then you just model it as a stochastic noise. So what it means, when you look at this quantity, it means that you're calculating an integral over some variable, and let's call this variable eta, which is defined for a domain. And then we have the function f of x, and then we have this epsilon, not epsilon, but yeah, epsilon. And let's assume that epsilon is a function of eta. And then there's a probability of epsilon, which depends on this eta. And then we have a d eta, like that. So this is one of the reasons why this quantity is going to be equal to 0, because we have set the mean value of epsilon to be 0. So we are assuming now that there is such a probability distribution which governs this quantity. So that's the probability distribution which is at hand. This function does not depend on this probability distribution. That's an assumption we are making. So f is a function of, for instance, x, and x is not a stochastic variable. And we've said that f is not a stochastic variable. So that means that we can pull f of x outside here. And that means that that expression which we had, this expectation value of f times epsilon, is just going to be f itself, because it does not depend on these probabilities. And then we have the calculation of the mean value here of p of eta, of d of eta. And we have defined this one, this quantity here, which is the mean value of eta, no, epsilon, to be 0. We just defined that. We assume that the noise is given by a normal distribution with 0 mean and a variance which is given by sigma squared. Okay? So the reason why we can do this is simply because we've made an important assumption that this quantities you see here, this quantity f of x, does not depend on the variables which define that probability. It's as if you are trying to calculate an expectation value for being along the x-axis, and your probability gives you only the probability of being along the y-axis. So that means that when you then calculate such an expression, there is no influence on the probability on being on the x-axis. Okay, So this means that when you add these things together, what we are going to get, since we also have this term which you see here, this term here, which does not depend on the probability, this is just a function itself. So what you're getting then is that this is going to be equal, so this expectation values which we put up here, this quantity which we have here, this one. So let's put the equality sign back. So this is going to be equal to f squared plus 2 times f times 0 plus sigma squared. Then we have a next term to take care of. So there's an expectation value which goes like 2 times y tilde. And this is going to be equal to 2 times the expectation value of f plus epsilon multiplied with y tilde. So what we get then is actually the following quantity. So this is going to be equal to 2 times, and then I have the expectation value of f times y tilde plus epsilon plus 2 times e of epsilon times y tilde here. Now, these two, y tilde and epsilon, are assumed to be independent of each other. So that means that this term here is a term, since the probability distribution we have defined depends on epsilon, defines epsilon, but it does not define, so let's just epsilon, e of y tilde. And we have defined this one again to be 0. So the assumption is that this function here, y, does not depend on the same probability as epsilon. So what we are left with then is, in total, what we are going to get when we collect all terms. This is a rewrite of the mean squared error. So we are going to have f squared minus 2 times f times e when we collect all the terms times y, the expectation value of y tilde, plus, and then I have the expectation value of y tilde. So I'm just collecting all the terms we put up, plus, let's see if you can see that properly, plus this variance of y tilde, that's the variance of the model itself, plus sigma squared. So this is essentially the kind of solution to the exercise next week with the assumptions we are making. Now, what we have now is something we can rewrite in terms of two expressions. So I'm going to collect this one, and I'm going to call that a bias. And you will see why we call it a bias pretty soon. And this is going to be the variance of the model itself. This quantity here is a quantity which we in principle don't know. So this is an assumption about the noise. And often when we don't know anything, we put it to 1 for the variance. Sometimes you have data on the variance, but in general you don't have. But we are going to leave that one out in the analysis here, because this is just a constant. And it's not that important for what happens when you look at this behavior here. So I should say one thing. This kind of analysis sounds like an overcomplication, because in many cases, what many practitioners do is only to plot this one and then just say that, hey, here, this is where I strike the compromise between my model complexity and the predictions I want to do. And it says that, okay, I'm happy with this error, and I'm happy with this model complexity. And this is what I want to give you. Use it for whatever it is good for. So if we now look at these terms, we have now the following. We are going to define this in terms of a term we call the bias, and then term which we call the variance, plus this sigma squared. So this is just the model variance. So what you have then is this term variance of y tilde. This term here is now given by the expectation value when we collect it of f minus the expectation value of the model. And this is called the bias. Now, this term here, we know that we cannot calculate this one. We don't know it. That's the one we are making an approximation to. So in order to be able to calculate, we make an approximation to the bias, because else we would not be able to evaluate it. So what we end up doing then is an approximation here, where this quantity, which we call the bias, or the bias squared, sometimes you will see it, we approximate that one with 1 over n of I equals 0, of n minus 1. And then we have y of I minus, so this, we approximate f with the output data. So in order to be able to calculate at all, the terms epsilon is just a constant which we add for the noise. And then we simply, so this is the way we often do the calculations in a practical way. So you can calculate the mean value of your model. So let's look at some interpretations of this. So when you are doing this type of analysis, this is normally done only on the test data. Only done on test data. And the example codes which you see online are all given by the test data, because that's what's interesting for us, just to see what happens when we now move into the overfitting region. So let's try to get some intuition about what is going on. So let me now show you an example. And this is one of those examples you will find in the lecture notes. So suppose you are aiming at this point here. This is what you want to reproduce. This is our holy grail. And then we have, so it could be something like you aiming at a specific point here. So the red one is what we want. So I'm going to give you now a result here, where this quantity you see here is the mean value of the model. So this is this expectation value. So you have trained a model, and this is your mean value. So if you now look at this parameter, which we call the bias, this measures the discrepancy between the model and the output. So now we want to reproduce this point here. So what would the bias be? Would it be large or small? So what is your, what does your intuition say here? It would be large, right? So this is what we would call a large bias. Okay? So we call it a large bias because you are biasing your model. You have, in a sense, in Norwegian, fordom, or you're putting too much weight on your model. And this is often something which comes when you have a low complexity. And it's understandable why it comes from a low complexity, because you are now you have a poor model, and that means that your prediction of the mean can be pretty bad for the model itself compared with the value you want to target. So low complexity means often that your model doesn't reproduce properly the data. Okay, so this is what we call a large bias. But let's now look at the other situation with the variance of the model. So suppose now that my model has a set of data points which look like this. So this is my model predictions. So if you now calculate the variance of the model, so the variance is the spread from the mean. So what kind of variance would you have here? If you go back to the expression which we have for the variance, if you look at that one, so let's just go slowly back. So the variance is nothing but this quantity. So it's the expectation value of y tilde squared minus the mean value. So if you now look at this image here, what would you expect? A large variance or a low variance? What's the popular vote here? So how many vote for small? Yeah, but suppose now these vary a lot, right? Yeah. What's the vote for large? Okay, so this is a situation which we call large bias and large variance. This is highly unwanted. We don't want to be there. So let's look at another situation. So let's just bring back. So this is what we want to find. And now I plot the mean value of the data. So this is my mean value of the model which I fitted, okay? So this is my E expected value of y tilde. And then I plot my data points here. Like that. So is this high bias or low bias? Low bias. So this is low bias, so that's fine. This is often something you will see when you made a fit to perfection. However, when you made this fit to perfection, the variance of the model can vary widely. So this would obviously be a large variance, right? So this is also unwanted. And that means that if we now go back, let me just go back to the Jupyter notebook and show you what you can expect. So if you go back to these examples, which we have in the notebooks. So if you look at this case here, your prediction varies a lot. And you see that immediately by looking at the plot, right? So if you were to calculate the variance of the model, it would be huge. And this is reflected in the quantities here. So if you go back here, scikit-learn has a functionality which is called cross-val score. So we're just making this polynomial fit, like you did in the exercises last week and the week before. And this is one of the functionalities which we are going to discuss next week, which is called the cross-validation. And it computes the score for you. So in this case here, you have defined the score to be the mean squared error. So it computes the mean squared error for you. And then when you look down here, it takes the scores, the mean value of the score. So this is the mean value of the mean squared error. So it does this cross-validation. It repeats the experiment many times. And then it sums up all the mean squared errors you calculated and takes the average of them. So this is what this does. The score is just the mean squared error, and just dot mean here, it's just the average mean squared error from all the experiments. And then it gives you the standard deviation of the mean squared error you're predicting. And you see in this case here, you have a horrible model. You predict your bias here is going to be extremely small because you are hitting the points here. So if you take the mean value of the model at the points you have trained, you're reproducing them almost to perfection. You see this? You're going through all the points, almost. So this would be a case with low bias, but you would have a horrible variance for the model. And this is what you see here is a clear example of overfitting. So when your variance in the model varies a lot, that tells you that there are such big variations in the model that you're going to make just horrible predictions. But if you only focus on the points which were included in the training, then you will say, hey, I'm pretty happy. I'm just reproducing what you gave me, right? This is just like us asking you to reproduce some stuff from the lectures without thinking, right? It's basically the same thing. So it's your critical thinking we are aiming at. So if somebody gives you this and you see you go through all the points, and you have this one where you don't go through all the points, but you still have a low mean squared error, and you also have a low standard deviation, which is a low, that's a spread in your model. So the standard deviation is nothing but the square root of the variance, which is the spread in the model we are making. Does that sound reasonable? So these are the kind of things we will see. And then you have to then strike a balance and say that, okay, in this case here, the model, the case before, we have a function which is given by the exponential squared, etc., plus some noise. I'm making a polynomial fit again, but here I'm calculating on the test data, only on the test data, and I'm using the bootstrap here. So this is an example with bootstrap, where I simply use this function, which you also have in scikit-learn, which is called resample. So the resample function reshuffles your data with replacement. And then you train the model and you make a prediction. And then you calculate the error for every type of resampling for the complexity. You calculate a mean error, a mean bias, and a mean variance. And you see now that this variance increases slow, not so much. And you could say now that at this kind of model complexity, which you have here, polynomial of degree 8 to 10, you could say that, okay, my mean squared error is small, but then it starts increasing. And you see now very clearly that the variance increases, and then obviously the total error. So the total error is just the sum of bias and variance. So one of the things which you're going to practice a little bit in the project as well is now to look at how the parameters beta change with increasing complexity. So what you will see is a big variation in the parameters beta. So the variance will increase for these parameters. And in the exercise this week, you have to calculate the analytical expression for that quantity. Then you add more complexity when you have a ridge regression with a new fitting parameter. But essentially, the kind of basic message you are going to extract is something which looks like this. So there is some kind of optimal model where you find the smallest mean squared error. Now, everything you do depends on the number of data you have. So if I now change this to 400, and I repeat the experiment 100 times with a bootstrap, and I fit this polynomial, then you could say, hey, I'm pretty happy. This is my total error. It's just a flat function. And with this kind of complexity, we can use a polynomial of degree 10 or 12 or whatever. And this is when you work with project one, this is a kind of a message you are going to convey to us who reads them about the fitting of the models you have done. So I wanted to give you this kind of link between overfitting and how we analyze it, and what kind of interpretations you can make. And one of the simpler interpretations, if you go back to the whiteboard, is a typical interpretation of this type here. So if you wish to, how to say, have a kind of overarching view on what low bias, high bias, etc. mean, this is a pretty simple picture. So the variance is the spread in your model from the mean value, and the bias is simply the spread from the mean value of the model and the data points you want to reproduce. And we made an approximation when we are calculating the bias because we don't know F, and we simply replace F with the data points. This is essentially the answer to exercises next week. I hope you don't get offended if we give you more of the answers. But these are things which are important to think of, also because many of you may not be too familiar with statistics because you have not taken a course in statistics. Okay, any questions so far? Something unclear? Or okay, so we are going back to the exercises now, but also many of you are also working with the project itself. And you can, hopefully you can do two things, or not exactly simultaneously, but I mean, you can reuse everything you do in the exercises in the projects. Okay, I'm going to stop here, and you will find a recording of this lecture online.